So this is my lecture 5. Lecture 5. So we will discuss controller design, controller design using board plot. So we will be discussing a lag lead. First we will be discussing lead, of course. Lead, lag and lag lead controller design. Lead, lag and lag lead controller. So simple low order controllers will consider first order control, lag lead, first order control, and lag lead, both first order lag, first order lead. So that's why it is a second order control. So these are the classical controllers that are normally used by practicing engineers. Also, it can be designed using Bode plot. So that is why it is well accepted by the industry. Very simple to design, and also it can be implemented in an analog fashion still. So now, what is the design objective here? So design objectives or design goals. Design goals are: one is steady state error specification, steady state error specification, phase margin, and gain cost of frequency. So these are the three specifications we want to meet here. So other specifications, other whatever objectives are there, for example, gain margin and all these things. So those we have to post check. So steady state error specification. Steady state error specification means some steady state constraints we have to meet: proportional error constant, integral error constant, ramp error constant. That means Kp, Kv, Kr, like that. Phase margin also we have to meet at some gain cost of frequency. So as you know, phase margin is related to damping ratio of the system. As phase margin increases, damping also increases. So phase margin is close to closely related to peak overshoot of the system. And gain cost of frequency determines how speedy a response is. If the gain cost frequency is more, then the speed of the response will be more. That means rise time will be less. So phase margin. So just to point out, phase margin, as phase margin increases, damping ratio increases. Damping ratio increases. So this actually zeta is phase margin divided by 100 approximately. So this is the relation. I think this relation Professor Sauropatra has already derived for at least for a second order system. Zeta is approximately phase margin divided by 100, phase margin in degree, and gain cost of frequency as gain cost of frequency increases, gain cost of frequency increases means rise time. Rise time decreases, that means the system becomes faster. So these are the three specifications we'll be meeting using both broad-based lag lead and lag lead controller design. So when lag controller is required, when lead controller is required, and when lag lead controllers are needed, so those things we will be discussing shortly. But before that, what is the control configuration here? That also I should say. So this is the control configuration we will be using. This is your plant GS, and this is your controller CS, and this is your reference input. So this is the feedback system we will be using. So this is your tracking error, and this is your controller output or control fault. So here CS will have two parts. This is your controller. This is a plant here. So in this design, board plot based design, CS we will assume consisting of two parts. One is thus just CS equal to will be assumed as K into HS. So K is your servo gain. So servo gain. So K can be considered as a servo gain. So this is used to meet steady state error constant. Steady state error specification. And HS is a normalized controller. So HS we will consider as a normalized controller. HS is a normalized controller. Normalized means steady state gain is 1. Normalized controller. HS has normalized structure. HS has normalized. It is a dynamical system, HS, dynamical controller, but it has normalized structure. That is H0 is equal to 1. Okay, so we will be considering, we will be designing HS. We will be seeing how to design HS, because the overall controller design will have two steps. One is based on steady state error specification. We will design K, and then so design of K and HS is decoupled because of this reason, this normalized structure. And then we'll be designing HS to meet phase margin and gain cost of frequency specification. So HS is normalized structure. So this is used to meet phase margin and GSF specification. So first we'll consider lead controller. So we are interested in HS only. So at the end, that means after discussing lead lag and lag lead controller, so we will be considering how to design K and how to given a problem, how to design K as well as HS together. So the lead controller HS. So the transfer function is HS. HS is of this type. HS is in normalized form S by A, whereby 1 plus S by alpha A, where alpha is greater than 1. So this is a normalized structure. You can easily verify H0 equal to 1. So what is the pole zero plot of this controller? You can easily see that is, suppose this sigma, this is j omega, So this will be your 0 location, say minus a, and as alpha is greater than 1, so pole will lie away from the 0 location. So this is your minus alpha a. So this is your pole 0 plot. This is pole 0 plot of edges. So now in lead controller, before that I should know what is the objective of lead controller. So lead controller, so lead controller is used, one, to provide phase lead along with gain attenuation, gain amplification at a desired frequency. So if an uncompensated system, or if the plant GS itself has poor phase margin, or the response of GS is sluggish, okay, then we'll use lead controller. So that means if a system, so this I should mark like this. If a system has poor phase margin or sluggish response, then we use lead controller. Okay. So sluggish response means low gain crossover frequency. So to increase the gain crossover frequency, we can use lead controller, and lead, it will provide phase lead. That means if a system is also suffers from poor phase margin, then also we will use lead controller. Okay. So lead controller, so it will provide phase lead. So what is the amount of phase lead it will provide? So phase lead. So phase lead, what is the amount of phase lead it will provide? It will provide some phase lead at some gain crossover frequency, at some frequency, and as well as it will provide some gain amplification. What is the phase lead it will provide? Phase lead phi is equal to, you can easily see from the transfer function. What is the phase lead? Tan inverse at frequency say omega, tan inverse omega by A minus tan inverse omega by alpha A. So this you can write phi is equal to tan inverse x minus tan inverse y. So tan inverse x minus y divided by tan inverse x minus y divided by 1 plus xy. That means omega square by alpha a square. So this means your phi will be tan inverse W into alpha. You can simplify it, W into alpha into, W into alpha, W into A, W into A into alpha minus 1 divided by W square plus alpha a square. Or you can also write this like this, phi equal to tan inverse alpha minus 1 divided by W by A plus alpha AY. It is not W, actually omega. Alpha A by omega. So what is the maximum phase it can provide? So for maximum phase of maximum of phi, so W by A plus alpha by W should be minimized. So for phi equal to phi m, W by A plus alpha A by W should be minimized. So this means d. So what is the frequency at which it will minimize? dW, d by dW into omega by A, d by d omega into omega by A plus alpha A by omega. This is equal to 0. So this means what? This means 1 by A minus alpha A by omega square equal to 0. So this means what? W equal to A root alpha. So this is the frequency. So I'll mark this is equal to Wm. This is the frequency at which this is at which phase will be maximized. So for this is the frequency at which phi will be equal to phi m. This is equal to what is the value of phi m? Where maximize, where phi m, that means maximum phase. How much maximum phase you will get? Tan inverse of alpha minus 1 divided by, so this will be, so if you put omega equal to omega m here, this will be root alpha plus, this will be omega m by root alpha. So this is alpha into, so this will be, yes, this will be also root alpha. So it will be alpha minus 1 by 2 root alpha. So this is the maximum phase lead. This is the maximum phase lead that can be provided by the phase lead or phase lead controller. Maximum phase lead. Maximum phase lead. So now what is the Bode plot of yeah, before that this phi m you can also write like this: phi m equal to sine inverse alpha minus 1 by alpha plus 1. So of course here alpha is greater than 1. So this is the maximum phase lead. So this you can also write. Now what is the Bode plot? So Bode plot of lead controller. Bode magnitude and phase plot. What is the magnitude plot? From the transfer function, you can easily see. So there are two there are two frequencies, two crossovers. One is omega equal to A, another is omega equal to two corner frequency. One is omega equal to A, another is omega equal to alpha A. So alpha is greater than 1. So omega equal to A. This is suppose 0. This is dB scale. Suppose omega equal to A. This is 0 dB. This is omega equal to A and alpha A. So how the plot will look like? So because of the 0, it will have unit slope here, and then again because of the pole, this slope will get nullified. pole at S equal to minus alpha, this will get nullified. This is the phase. So it will provide gain amplification. Now, what is the, so this is your mod H omega. What is this magnitude? This magnitude is, you can see this magnitude will be 20 log of alpha. So this is in log scale, and this is in dB scale. So this is 20 log alpha. Alpha A by A, 20 log of, what is this? It will be 20 log of alpha A by A. So that's why 20 log alpha. So now phase plot. This is asymptotic plot I have drawn. So you can also draw the pure plot. So this is your plot. This is 3 dB cut of 3 dB difference will be there. So this is your actual plot. This 3 dB. So this is your actual, and this is asymptotic. So we are not bothered about whether it is actual asymptotic or anyone will suffice. So now, what is the phase plot? Phase, if you draw, so phase plot, phase lead. So at omega equal to 0, phase will be 0, and at omega equal to infinity also it is 0, and it will be maximum at omega equal to A root alpha. So that means it will be like this. It will be like this. So this will be your phi m. What is the frequency? This frequency is, this is your A, this is your alpha A, this will be your, this is your A root alpha. That means geometric mean of A and alpha A. So that is your frequency at which phase will maximum phase it will give. Okay, so this is your phase phi. This is your phi m that I have already mentioned here. This is a phi m. So now, so here you can easily see what is the magnitude. Okay, magnitude Hg omega you can write as it is gain Hg omega equal to what? Alpha into root under omega square plus s square divided by root under omega square plus alpha square s square. That you can easily, if you put s equal to g omega in this transfer function, and if you take mod, then you will get this one. Now alpha is greater than 1, but how much alpha in practice is allowed? So in practice, alpha is actually less than 20, it is assumed. This means that is phi m, maximum phase lead is assumed to be, if you take alpha equal to 20, then the corresponding phi m, if you found, it will be 64.8 degree approximately. So alpha less than 20 is allowed. If you make it alpha much more, then what will happen? Then this pole location of the controller will be far away from imaginary axis, and it will be very much susceptible to noise. Also, we will see later that this controller can be, when we will do analog implementation of this controller, one amplifier is needed, one active amplifier. So that active amplifier gain is assumed to be less than 20. So if it is more than 20, gain is needed So then amplifier will cause some problem. The high gain amplifier is what will happen? High gain amplifier in a controller, if you use, then noise then the loop gain will increase. Then the loop gain will increase means well, loop gain, forget about loop gain. If the controller gains are high, then the control effort will be more. So those problems will occur. Control effort will be more, and also if the controller gains are high, then control effort will be noisy. Control input will be noisy. High gain, it will be highly sensitive to noise. So that's why this normally this is used, that alpha is less than 20. So we have to design in such a way that the phase lead controller will provide maximum phase of around 60 degree or 65 degree maximum. Now how to design the design approach, algebraic approach we will be using. So in NK Sinha book control system, so I will be following for this portion, I will be following NK Sinha book, control system design by NK Sinha. In that book only this algebraic technique is there to design lag lead and lag lead controller. In all other books, those design is little bit iterative. So that's why I will not follow all other books. I will follow only NK Sinha book. Is a algebraic method is there. That method I will follow. So algebraic method method to design algebraic method to design lead controller. Okay. So now what is the objective? So objective is what? Objective, as I said, so objective will be given. Objective will be given phase lead of phi c say, and gain MC, of course, in dB at some frequency, that is gain crossover frequency, at some frequency which we want to be gain crossover frequency of the compensated system, at frequency omega c, obtain alpha and A. So ultimately alpha and A parameters we have to obtain, and so we are supposing that we will be given what is the amount of phase lead you need. So how to determine how much phase lead is needed, how much gain is needed, at what frequency, that is different problem. That we will consider later. But now we will be considering that phase lead, how much phase lead is needed and how much gain amplification is needed. Those things are given, and also at what frequency those are needed are given. So we have to determine the parameters of the controllers, or parameter of the normalized part of the controller, that means alpha and A. So now what is the solution? So solution, so this method is very important. The algebraic method. So let Q equal to tan of phi c. So what is phi c? Phi c we have already obtained. What is your tan of phi c? So phi c is this one. So tan of phi c will be what? Tan of phi c is omega into A into alpha minus 1 divided by omega square plus alpha square. So this means Q equal to tan of phi c is what? Omega into, so omega into alpha divided by omega into alpha into alpha, omega into a into alpha minus 1 divided by omega square plus alpha square. Omega square plus alpha into a square. So this means what? Q equal to, you can write, if you divide numerator and denominator by a square, you can write omega by a into alpha minus 1 divided by, at omega c actually. So I'll write omega c. So omega c by a divided by alpha minus 1 divided by omega c by a whole square plus alpha. So I can consider omega c by a as a normalized frequency, that is omega c bar. Q equal to, suppose, omega c bar into alpha minus 1 divided by omega c bar whole square plus alpha. So what is omega c? Where omega c bar equal to omega by a, that is normalized frequency. Also let, well, so what is MC now? So MC will be at omega equal to omega c. What is the MC? That we will get, MC will be equal to mod of 8j omega c. So what is your mod 8j omega c? This means MC equal to, what is your mod 8j omega c? Mod 8j omega c is alpha into root under omega c square plus a square divided by root under omega c square plus alpha square a square. This you can write like this. This means your MC equal to alpha into your, so omega c bar, the normalized frequency, plus a square divided by root under omega c bar square plus alpha square. So now we are, suppose we are defining, let, so well, before saying that, I will just compute this one. 20 log of, that means in dV, 20 log of MC equal to how much? 20 log of MC, that means MC, well, I should not use MC here because MC I have considered in dV. 20 log of MC bar, this is equal to what? 20 log of MC bar, this is gain. 20 log of MC bar is what? 20 log of MC bar will be equal to 20 log of 20 log of MC bar is equal to 20 log of alpha root omega c bar square plus a square divided by root under omega c bar square plus alpha square. So this, so this you can write well. So now, okay, I think this is not needed. This is not needed. This is not needed. So this is MC in normal scale. MC bar is normal scale. So MC is what? MC is MC in dB. So MC equal to what? 20 log of MC bar. This is because MC in dB. So MC is 20 log of MC bar. So this is equal to what? So 20 log of MC bar. Write like this. I think what is your MC? MC expression is correct. MC expression, yes, alpha into this one. So now what is your MC bar? 20 log MC bar. So this is equal to 20 log of alpha into root under omega c bar square plus a square divided by root under omega c bar square plus alpha square. So this you can write, this implies MC equal to, you can write 10 log of, you can write from there. If you multiply 2, so it will be 10 log of this square, that means alpha square into omega c bar square plus a square divided by omega c bar square plus alpha square. Yeah. So that means MC by, so now let C equal to MC, C equal to 10 to the power of MC by 10. So this means C will be what? Alpha square MC by 10, so log 10, so 10 base, so this will be, so this term will be C, then C equal to your alpha into, so MC is given, MC in dB is given, so then C we are defining as 10 to the power MC by 10, so then C will be what? Alpha square into 1 plus alpha square into alpha square into, so this will be I think 1. When you are normalizing, this will be 1. This will be 1. Also this will be 1. When you are normalizing, this would be 1. This will be 1. So alpha square into omega c bar square plus 1 divided by omega c bar square plus alpha square. So now suppose this is some equation number we have to give. Suppose Q equal to this one you consider as equation number 1. This is suppose C equal to this one you consider as equation number 2. And then from 2, what we are getting from 2, you can get what is W omega c bar square. Omega c bar square you can compute. What is your omega c bar square? You can express omega c bar square. If you check it, this will be alpha square into c minus 1 divided by alpha square minus c. So this is suppose equation number 3. Then what will you get? This omega c bar square, if you substitute in your this expression, is omega c bar square, if you substitute in this expression, now from 1 what we are getting, from 1 q square equal to omega c bar square plus alpha, omega c bar square plus alpha square, whole omega c bar square plus alpha, omega c bar square plus alpha, this whole square into q square. This is equal to omega c bar square into alpha minus 1 whole square. So now if you substitute omega c bar square, so if you this expression, now if you substitute omega c bar square in this expression, substituting 3 in, suppose this is your 4, in 4 we get, what will you get? You will get this equation like this: q square, please check it, q square into omega c bar square base, so q square, then omega c bar square is alpha square into c minus 1, then plus alpha into alpha square minus c, this one, this whole square, this is equal to alpha square into c minus 1 into alpha square into c minus 1 into alpha omega c square. Omega c square means, so here double square is there, so here alpha square minus c will get multiplied into alpha minus 1 whole square. So if you, it is very algebraic in nature, so if you just check, you will get it. So this can be further simplified as, if you simplify this expression, it will be like this: q square into alpha square into alpha minus 1 whole square into alpha plus c whole square. This is equal to alpha square into c minus 1 into alpha square minus c into alpha minus 1 whole square. Now alpha is not equal to 0 and alpha also not equal to 1. So from here you will get like this. You can simplify it: q square into alpha plus c. So this will get cancelled. This will get cancelled. So that means alpha plus c whole square. This is equal to c minus 1 into alpha square minus c. So why? Because alpha is greater than 1. So that's why we have cancelled these things. If alpha is equal to 1, you cannot cancel. So this will imply, this equation you will get q square minus c. If you simplify it, q square, then you can, that means if you simplify this kind of quadratic equation, you will get q square minus c plus 1 into alpha square plus 2q square c into alpha plus q square c plus c minus 1 into c. This is equal to 0. Please check this equation. So just, you can easily see here, if you take if you square it up, then you will get q square, and then alpha square coefficient, another minus c will come from here, and then so my plus 1 will come from here, then from here to 2q square alpha c will come from here, and then q square c square will come from here, q square c square, and then c minus 1 into c will come from this one. So okay, it's fine. So now we have to show what is given to us. Given is q and c. Q and c, because q, what is c? C is your C is your 10 to the power mc by 10. Mc is given, mc in dB. So that means C is given. And what is your Q? Q is your omega C bar into alpha. Well, Q is your this one, tan of phi C. So phi C is given. So phi C is given. Phi C given. So phi C given and MC given. So MC given. So phi C given, MC given means your Q and C are known. So you have to find alpha. So but alpha is a positive. Alpha means alpha greater, not only positive, alpha greater than 1 is needed. So now what is the condition under which a solution, a valid solution of alpha will exist? So that you have to find. So so suppose this is equation number 5. So from 5, so if you compare this equation with standard quadratic equation ax square plus bx plus c equal to 0, then for a positive solution, because alpha is anyway it is positive. So for positive solution to exist, what should be the condition for positive solution to exist? For existence of a positive solution of alpha, what should be condition? What should be the condition? And your q square c is greater than 0. So q square, a positive root will be there if so what is the root for a standard second order equation? Ax square plus bx plus c minus b plus minus root under b square minus 4ac divided by 2a. So for positive, one positive solution, if has to exist, root under b square minus 4ac should be greater than greater than b. So b square minus 4ac greater than b. So if you apply, b is here positive, so q square c positive. So if you apply that one, then you can show that for existence of solution of alpha, this should be satisfied. A into c should be less than 0. So that means q square minus c plus 1 into q square c plus c minus 1 into c should be less than 0. Now as c greater than 1, c is 10 to the mc by dB. mc is not, mc is greater than 0. So c is greater than 1. So c is greater than 1 means now as c is greater than 1, we have this term is greater than 0. That means we have q square c plus c minus 1 into c greater than 0. Then greater than 0. So one must have, so one should have q square minus c plus 1 should be less than 0. So this implies your q square should be less than c minus 1. So this is your necessary and sufficient condition, N and S, necessary and sufficient condition for existence of a positive solution. Not only positive, I should say valid. Solution. Valid solution valid solution, because alpha is greater than 1. So alpha is greater than 1. So valid solution will exist. Valid solution, that means at least valid means here positive, actually positive solution. So if a given combination is there, then this is necessary and sufficient condition for a valid solution to exist. So then once you get the solution, once you get the solution, then what is your alpha? So then alpha can be determined. Then A, alpha and A you have to find out. Once alpha suppose determined, then A can be determined. Then A can be determined from, so omega bar divided by A equal to omega C. So omega bar, so here you see, so how you can get A? Omega C is what? Your omega C bar. What is your omega C bar? What is your omega C? Yes, omega C bar is your omega C divided by A. So A equal to omega by omega C. What is your omega C? So your A will be, how to determine A? So here your A. So from this expression you will get actually here, this is omega C square divided by S square equal to, from 3 actually, omega C square divided by S square equal to alpha square into C minus 1 by alpha square minus C. So then can be determined from 3 as A will be equal to omega C divided by alpha, omega C divided by alpha into root under alpha square minus C divided by C minus 1. So this expression is also very important. So this is for computation of A, and this expression is for computation of alpha, and this is your necessary and sufficient condition for existence of solution. Okay. Now one example we will consider. Simple example. So here your one example. Determine the parameters of a lead compensator, lead controller HS, that will provide a phase lead of 45° and gain equal to 10 dB at omega C, as angular frequency equal to 8 radian per second. This is the question. Now how to solve? Just we'll apply the results that we have derived. So here, what is phi c? Phi c equal to 45 degree. What is your MC? MC in dB is 10 dB. And what is omega c? Omega c is your 8. This implies, what is your Q? Q equal to tan phi c. Tan phi c, that means tan of 45 degree. This is equal to 1. C equal to what? 10 to the power MC by 10. So that means this is equal to how much? This is MC is 10. So this is 10. And so this will imply, so what is the condition? C greater than, C is 10, C is greater than Q square plus 1 is satisfied. Satisfied. So this means lead compensator exists. So now how to get the parameters? We have, just we will solve the quadratic equation. Q square minus C plus 1 into alpha square plus 2Q square C into alpha plus Q square C plus C minus 1 into C. This is equal to 0. So this implies if you substitute these values, it will be like this. Please check it. 8 alpha square plus 20 into alpha plus 190. This is equal to 0. So a valid solution of alpha is positive. So it will have two solutions, one positive, one negative. Of course, negative you will not consider. So positive solution you will consider. So positive solution alpha. So this will give you alpha equal to 6.2812. Please check it. And A will be equal to A. Then you can obtain as omega c by A into under alpha square minus C minus 1. So this is equal to 2.304. Okay. So then ultimately your HS will be ultimately your alpha into S plus A divided by S plus alpha A. So this will be equal to 6.2812 into S plus 2.304 divided by S plus 14.472. So this is your HS. Now the question is how to realize the PD controller in an analog fashion. Suppose we have given a problem, we have determined your A and alpha. So how to implement this transfer function? So you can implement. So an implementation. Implement digitally you can implement, but analog fashion nowadays all controllers are implemented digitally, but still the beauty of this lag lead controllers or simple controllers like this is it can be analyzed, it can be realized or implemented in an analog fashion easily. So this is one implementation diagram. This is your amplifier alpha. This is C capacitor. This is suppose R1, this is R2, and this is suppose V1. This is suppose V2. Okay, so V2 this voltage, V1 is this voltage. Then I write here another quantity. So this is V2. So this alpha, this amplifier can be a differential amplifier. So this can be realized using op-amp like this. So So gain will be 1 plus 2ir1. So this is a negative terminal. So in this way you can design alpha. So what is your V2 by V1? V2 by V1 will be equal to, you can easily see alpha is that factor. And what is the current? Current will be, the current through this one is your V1 divided by R2 plus R1 parallel 1 by CS. So now what is the voltage then? 1 by this one. So voltage will be then R2. V2 will be R2 divided by this into. So if you simplify this, this means V2 by V1, this is equal to alpha into R2 into R1 plus 1 by CS divided by, I will simplify it, R2 into, please check it, R1 plus 1 by CS plus R1 by CS. So this you can simplify further like this, V2 by V1, this is equal to, okay, so I'll go to next page. So this will imply V2 by V1. This is equal to alpha into R2. Alpha into R2 plus R1 R2S. Just I have multiplied R1 R2 into CS. And this one will be R1 plus R2 plus R1 R2 CS. So this you can further simplify like this, V2 by V1. So V2 by V1 equal V2 by V1. Actually, I want to show that it is in the form of lead controller transfer function. V2S by V1S actually. S, these are all S. S I am not writing. So this is equal to your alpha into S plus 1 by R1C divided by S plus R1 plus R2 by R1 R2 into C. So now, so this can be written in that form, V2S divided by V1S, this is equal to alpha into S plus A divided by S plus alpha into A. So what is your, where A is what? A is equal to 1 by R1C and alpha equal to your R1 R1. So if we divide by 1, so R1C will cancel. So R1 divided by R1 plus R2 divided by R2. So R1 plus R2 divided by R2. So which is less than 1. So this means, so here alpha should be less than 20, as I said, because of this, because it is a differential amplifier. So high gain amplifier will cause that realization problem as well as this, your noise susceptibility problem. So this is about lead controller. So how to design given a system, what is the phase margin, how much phase margin you did, what is the gain cursor, all those things we will consider later. But this is the lead controller transfer function I have designed, and the lead controller transfer function I have considered is a first order controller. And also we have seen how to design the parameters using an analog approach. So once again, I will see if there is any minor error. For phase margin, surface response, then we use lead control, that's fine. Provide phase lead along with gain amplification at a desired frequency. Okay. So this is omega. Frequency at which I is maximum here. Okay. This is alpha is less than 20 algebraic method to design lead controllers. So this is very important method. So in Enkesina book, this is there. So this equation is very important. Algebraic equation, quadratic equation for solution of this quadratic equation under for alpha for each alpha should be greater than 1. That is very important. What is the condition? So this is the condition. Q square minus C plus 1 into Q square C plus C minus 1 into C less than 0. That means ax square plus bx, ax square plus bx plus c. If you consider, and if b is positive, if b is positive, then the condition for positive solution to exist is root under b square minus 4ac should be greater than b. Will be greater than 0, so that means a into c should be less than 0. So that's why this is your a and this is c. That's why this here I have written this one. Positive solution. Positive solution is important. And here c is greater than 1. C is greater than 1. Yes, and c is greater than 1 and q square c positive. That's why. So that's why this is also greater than 0. So this is the condition for the existence of a positive solution, for existence of a positive solution. Okay, valid solution. Okay, I think if there is any error, please let me in the doubt clearing. Let me know in the doubt clearing class, and also if I found later if any minor error, then I will also let you know. Thank you.